Okay, so here we have a pulley for a car engine, and as a transducers, we will use one impact hammer and two accelerometers. All are connected to our 35 analyzer. I'm gonna describe you now the test objects. This pulley has a rubber part inside to damp the torque ripple. So it's a good for EMA because we have a free condition now. To the symmetrical shape, we need to use multiple references, at least for radial direction. So one measurement here, why not one measurement here? And to have this displacement in vertical direction, we can add one more here. I'm going to show you the transducers. So one 3-axial accelerometers here, so we use two inputs, and one monoaxial accelerometer, so one input here. So in total, 3 references. So let's define how to hit the pulley with the impact hammer. So on this cylinder, the belt cylinder, I will hit in 1, 2, 3 circles, 8 locations each, in radial direction. For the upper disc, I will have 1, 2, 3 circles, 8 locations as well, for the vertical direction. Before starting acquisition of root points, we need to create a geometry in accordance with the pulley shape. It's possible to import CAD files such as IGES file, but here I will show you how it's easy to create a geometry from scratch. The pulley is roughly composed of one thin cylinder for the belt and one disc on the top. Let's first create a cylinder and then a disc. In Modal software, in the Shapes library, let's select cylindrical shape with the same length for both directions to get cylinder shape. And maybe one segment, let's see what happens. Yes, happen. And maybe add an additional segment to have 3 nodes on the shape. Rename it. Now the base cylinder is ready. For the upper disc, let's add an elliptical shape. Yes, we have to get a circle. We can rename it first, and then let's set the long and short axis to 10 to have the same diameter than the cylinder belt, and fly over the mouse of illustration to get more information about properties. Now let's remove the nodes in the center, since pulley is empty in this area. Just select and press delete through the keyboard. That's very intuitive. Okay, now there are 2 separate shapes. At the junction, if you zoom in, there are repeating nodes. So let's use the features validity check to fix this. If we look at the node list, there is gap between index and node number, because we removed node previously. To fix any gap, let's use the renumber feature to get our order list. Now it's matched and geometry is ready. I'm going to talk to you about coordinate systems. In Modal software, coordinates are linked to each shape. I mean, cylindrical coordinates when shape is a cylinder, it makes sense. It's really convenient that coordinates are smartly linked because accelerometers measure response in the direction perpendicular to the surface. So when the local coordinate is linked to each node, Cartesian system is usually used. Since directions do not match the measuring direction, trigonometric projections are needed. In Modal software, local coordinates are linked to the shape instead of each node. On this animation, it's clear that accelerometers, direction, and measuring direction are matched. Now, geometry is ready, and we can go to the acquisition part. To start acquisition setup, let's select the transducers that will be used, impact hammer, and 3 accelerometers as a reference. Load from the database. Here it is. Before going to the sequence settings, let's check that transducers are properly connected to the right analyzer input. Let's now configure the set sequence. Node 1 and 16 are reference node. X-axis for radial direction. Here we don't care about transducers, only DOF, degree of freedom. For the roving DOF, we will build up sequence in 3 steps. 24 nodes, X direction for the node for the belt cylinder. Yes, so batch add. We can rename it belt cylinder. So the first step. The second step, to build up the upper disk, 16 nodes in vertical direction, Z axis. And at the end, we will add 8 nodes that are common to the both shapes, the repeated nodes we got previously. Okay, so the number of set is 1 because of 1 hammer for each set of measurements. Yeah, for the repeated node, we need to increment 3 by 3. We can rename it to complete this geometry. Okay, so now it's important to check if sequence is right. If directions are correct, it's easy first for all nodes. Yeah, we can see in the green vector as a roving DOF and the red vector as a reference fixed DOF accelerometers. Okay, so it looks nice and correct. Let's now see how to tune the metrology part. So we need to analyze modes up to 5 kHz with a large number of lines to get a good damping estimation. We will hit 3 times and we don't need any wandering so far. For the trigger, let's select inputs and automatically the software will be find the channels for the hammer. Okay, let's set the threshold, the pre-trigger, and it's time to display and save the data we will need during acquisition. All channels on the same graph to check any double impact on the trigger block, and all FRF in the same graph, currents as well, and now it's okay. So now let's use the outer range features to automatically set the hammer threshold and in the same time the range peaks. So click on outer range. 2 seconds is the time to go to the parts. If my parts is far, it's convenient to make to use more time, and 4 seconds it's the time I have to hit after the beep on my structure to set properly the range peak and to avoid any overload. So okay, so now the range are up to date. Let's do the last check to make sure that the measurement parameters are properly set. In terms of, I guess, I would check the current, the trigger block, especially the length, if we need or not windowing. So let's do a first measurement. So I press run, I hit 1 point. Okay. Okay, so the signal is properly damped, so no need to use any windowing. The clearance, it looks very good, and so for me it's okay. Now we're ready to start the test sequence. So before that, so the geometry give me at any time the nodes where I need to hit. So so I focused on the green vector, and it's also helpful to use features like auto run to automatically switch to the next step. The double hit rejection in case of double impact, and the overload rejection in case of strong hit. So let's start from the set 1. So I hit on net 1. So it's better. 2. 3. 4. Only one hit to go fast. I previously checked the clearance. The clearance was good, so there is no way now that the clearance will be bad on this type of parts. So node 7. Now I use, yes, so now it's hang because if I look at the trigger block, we clearly see double impact. That's why the hills get red, and I have to redo this hit at node 8. Okay, 9. So now I don't want to wait for the end of all my mesh. So I'm going to check the consistency of my data from my 9 points. So I send the frequency domain data into my software in order to display the deflection shape of a part of my structure. I double click on the frequency domain section and I select, for example, the first resonance. So with the cursor here, and to check if there is no big error in terms of dove. Okay, so it looks nice, so I can go ahead and complete the last point of my geometry.